People really do miss you, Christian. Yeah, we hope you're feeling okay. You know what? We've got notes 4.4. We're going to piggyback on to what we had talked about before. Non-homogeneous. Wow. Right there, that's the game changer, isn't it? Non-homogeneous differential equations. Something called the Undetermined Coefficients method, day 1. If your non-homogeneous differential equation, your right-hand side is not 0, here's the crazy thing. First, pretend it was equal to 0. And do what you were doing so very, very well last part of chapter 4. Solve for that complementary function and go ahead and get your answer to that homogeneous differential equation. Then we're going to, this is the new part for number 2. It says find a particular solution. This is brand new. And then join them together. So let's go ahead and see what's going on. First off, like we said, to get you started, let's just pretend that we've got the right side equal to 0. You could say, hey, we've got the left side, y double prime minus y prime minus 2y equals 0. Would you agree if we assumed that a general equation would, a general solution would look like y equals e to the mx, that a characteristic equation would look such as this, m squared minus m minus 2, right? And then we'd factor it, right? And we could say, well, let's see, I think it does factor, doesn't it? What do we get? M minus 2 and m plus 2. And without too much work, kids would say, well, m would equal 2, m would equal negative 1. And without hardly any work at all, we'd say, well, we'd have some constant e to the 2x plus a second constant e to the negative 1x. And, back in that first part of chapter 4, we'd be done, right? Well, beautifully, we're halfway there. We've got y sub c. We've taken care of number 1 up here, but now we've got to deal with step 2. Find a particular equation. A particular solution, I should have said. Pardon me. So we're going to look at this right-hand side. We're going to look at this right-hand side right here and say, look, everything has constants in it, and we're only going out to a second degree. Let's just assume for a moment, this is undetermined coefficients. Let's assume that a quadratic equation, y equals ax squared plus bx plus c, would satisfy that differential equation. Now, kids could think, well, how in the world would you ever think about that? Well, think about it. If I were to take a second derivative, first derivative, and the original function itself, combine them all, would you believe if you did that, you would get a quadratic, perhaps, that might look like 4x squared? Right? Think about it. First derivative, second derivative. Help me out. What is my first derivative of ax squared plus bx plus c? What would that look like? 2ax. Yeah, 2ax plus b. Help me out. What's my second derivative then going to look like? Just a 2a. And then we're going to come back to the original problem. We're going to come back right here, and we're going to say, you know what? Plug those in. Plug that in here. You'll get 2a. Minus, right here I'll have 2ax plus b. Minus 2 times my original y. Well, the y here is ugly. Ax squared plus bx plus c equals, and then I'm saying the right-hand side should look like 4x squared. You can think, my gosh, this looks to be a real mess on the right-hand side. You bet. Look, I'm going to distribute that negative. I'll get a minus 2ax and a minus b. I'm going to distribute a negative 2 over here, and I'll get negative 2ax squared plus minus 2bx minus 2c. And maybe right now this is going to unlock what we're about to do. I'm going to look at the right side as 4x squared plus 0x plus 0. I'm going to say the right-hand side is a quadratic equation, and so is the left side. You see, the left side, I'm going to start off and say, you know what? Where do I have squared terms? You'd say, well, you know what? You don't have too many of those. You only have an x squared term over here. So I'm going to just rewrite that as a negative 2ax squared. And I'm going to keep that in yellow, okay? And then you'll say, well, next, what else do we have on this left-hand side? Well, guys, it won't take you too long to see that some of these terms actually have an x in them, right? Some of these terms have an x in them. And it wouldn't take you too long to say, well, hey, you know what? I could combine those. Actually, and let's see here. If I factor out an x, guys, I'd be left with a negative 2a minus 2b, and here's my x. Say, kids might ask, why are you doing that? I'm trying to group like terms together. Finally, you could say, well, wait a minute. Then you've got some terms that don't even have an x or an x squared in them at all. That would be like your constants, of course. You could say, well, that's going to be a 2a in blue minus a b minus a 2c. You could say, well, okay, I guess I see what you've done. You've grouped your like terms together. But would that be of any help? Well, if a quadratic equation on the left is equal to a quadratic equation on the right, we could do what's known as coefficient analysis. Whatever is in front of x squared must be in front of x squared on the other side. Do you see that? Negative 2a must equal 4. Wow. Whatever's in front of x squared must be in front of x squared. Now help me out. What would a have to equal then? Negative 2. And then you'd say, well, whatever's in front of x, that's negative 2a minus 2b, that's going to have to be whatever's in front of x over here. Guys, that's 0. Negative 2a minus 2b, that has to equal 0. I've got good news for you guys. You know what a is. You know a is negative 2, so I could say negative 2 times negative 2. Well, wow. Doesn't take too long to see that's 4 minus 2b equals 0. So 4 would equal 2b. Guess what b is equal to? 2. Hey, all of a sudden I have a and I've got b. And then I come over here to my constant. 2a minus b minus 2c. Well, the constant on the left would have to equal the constant on the right. But guess what? Now I know what my a is. I also know what my b is. And then I can solve for c. Hey, look at that. Without too much work, you're about to find the quadratic that you're looking for. Tell you what, I'm going to add a 2c to both sides and quickly see that c equals negative 3. So a is negative 2, b is equal to 2, and c is equal to negative 3. So what we assumed in the beginning, y is equal to ax squared plus bx plus c, and that, by the way, is my particular solution that I'm guessing. I could say, well, wow, now I believe that in particular, negative 2x squared plus 2x minus 3 is going to do the trick. It's going to solve that differential equation. But as we move on, we're going to say, wait a minute, we have to get our general solution. It's going to be the solution to the homogeneous differential equation plus the particular. That's where they get joined together, guys. So that's really what we're doing today. We're going to solve the homogeneous differential equation, pretend there is a 0 on the right side. And then we're going to look at the right-hand side, knowing it's really not 0. And we're going to say, well, could we have an intelligent guess as to what a particular solution could be? Take some derivatives, plug it in, and see if it checks out, and find out what those general coefficients are, and then we'll be good to go. Okay, any questions so far? All right, let's go and start taking a look at our second problem here. And you might guess that, we're going to get started with the homogeneous setup. We're going to say, hey, just like we did last week, let's just keep it nice and simple and say, hey, I certainly believe that we're going to get a solution here. Our characteristic solution would be m squared minus m minus 2 equals 0. And once again, as we factor this thing out, you can see we'd have our m squared minus 2, m plus 1, and it doesn't take long to get m equals 2, m equals negative 1, and to say, hey, for our homogeneous solution, we'd come up with this. And we're pretty much halfway there. Okay, we doing okay? But now you look at the right. And on the right-hand side, kids can quickly and understandably say, now wait just a moment. Before, you had a quadratic, and you had every reason to believe that if you're taking first derivatives, second derivatives, and the original function and combining them, that a quadratic would be such that in that combination you would still have a quadratic. Here, we're thinking, wow, when you have a trig function like sine or cosine, what could you assume could be a general solution? And I'm going to make a bold pronouncement right here. I'm going to say, let's assume it's a combination of sine and cosine. The reason why I'm going to put sine and cosine together is that when you take derivatives of either one of those, you tend to get the other function as a result, don't you? And in the combination of those two, maybe taking a first derivative and a second derivative and the original function, combining them all, it's very possible that a cosine could cancel out. So in general, guys, what you want to do is, for trig, join those two together. Let's go ahead and try to take a derivative. What's the derivative of a sine of 2x? Don't forget the chain rule. Yeah, 2a cosine of 2x. The derivative of cosine is negative sine. So the chain rule still comes into play, but here you go. And then we'll say we'll take another derivative, because I'm going to check. I'm going to plug that all in. Second derivative, well, the derivative of cosine is a negative sine. So out comes a negative, out comes another 2. And you could quickly confirm you get negative 4a sine of 2x. Derivative of sine, it's not going to have another negative come out, but another 2 will come out. Derivative of sine is cosine. So there you have it. You've got your first function, y, your derivative of it, and your second. And we're going to plug all of those in right in here. This is a perfect time to stop the video. We're going to have to pick it up with a second part.